So we left here in our previous video. We learnt about in case of a spherical shell of charge, a conducting shell of charge which is hollow also. These are the electric field and the potential. We have also learnt a very important conclusion that though the field can be zero, the potential is a constant, because when we are going inside from surface, when we are actually bringing a charge from infinity to the surface, we need to do work. And when, as it is a conductor and electric field inside the shell is equal to zero, so when we are moving from this surface towards the center, no additional work is to be done on the charge for this motion of the charge. And this is the reason why the potential is constant from surface to the center of this spherical shell of charge. Now, let us revisit the Gauss's law. This is Maxwell's equation, one of the Maxwell's equation, though it was originally given by Gauss. Now this is the closed surface integral. This symbol is for closed integral. This is electric flux density. This is a differential surface we have chosen for the integration. Rho v is the volume charge density. Now, do we have any kind of differential form of this Maxwell equation or Gauss's law? The answer is yes. But let me tell you one thing, why the differential form is important. Why we actually go for a differential form of this law? That is because in order to incorporate the localized effect of a charge, we need the differential form, because the differential form actually accommodates the concept of smallness, the concept of localization. Now suppose we put a line charge here. A charge is distributed through this line. This pen, for example, this is a line charge, and for the effect of this charge over here in this region, we consider differential form of the law. But if we consider a very large surface, because this effect will of course propagate. So if we consider the large surface in for example, if we want to consider the effect of this line charge throughout the entire copy, then we need to incorporate the totality of the effect, and then we will choose the integral form. So the conversion between the two forms of the laws, from integral to differential and from differential to integral, is very important. Now, differential forms are often used, actually extensively used in case of numerical problems, because we can understand that if we have the localized effect, we can really find out the global effect also. So from differential form, we will be able to find out the localized effect without too much rigorous calculations. Now we are going to introduce the concept of divergence. Suppose I am taking a Cartesian coordinate system. This is x, this is y, this is z. For convention, this I have marked according to the convention. This is a right-handed Cartesian coordinate system. We can mark this as x, this as y, this as z also. Now if we choose a differential volume element, then the volume of this cube will be delta v equal to delta x, delta y, delta z. I have zoomed in this volume. So suppose that the cube is sitting here. This center is p. P is of course a function of x, y, z. Along this direction y changes, along this direction x changes, and along this direction z changes. So this is delta x, this is delta y, and this is delta z. This is the volume of this element. Now we consider actually this has 6 surface: front, back, right, left, top, bottom. But for calculation purpose we'll choose only the front and back surface, because if we can do calculation for one surface, then we can do it for other surfaces also. Now if we choose this surface where y and z varies, and this is along x direction, so for the front surface the unit vector is like this, and this is along a positive x direction, let's say. So for the back surface, the direction of the surface will be along negative x direction, and we choose this point. Like here we have some at some point here we have some x value, and just at the front surface, suppose I approach in this direction delta x amount, and along the back direction again the delta x amount, then it will be so I am landing at a point where x coordinate will be x plus delta x by 2 and y coordinate will be x minus delta x by 2. And for front surface, if we choose the surface coordinate, the surface area, differential surface area, then the differential surface area, as this is along x direction, I have to write dsx, and as y and z changes, so we write this as delta y delta z, and direction of this area is along a plus x direction. Similarly for the back surface, this is the surface area. As it is a closed surface, this one is a closed surface, so I can easily apply the left hand side of the Gauss's law. I have not written the Gauss's law here. Anyways, I can easily write the integration of d dot ds here for this surface. Now this point P is the coordinate of the point is xyz, so I am moving a total of delta x amount, delta x by 2 in the forward direction minus delta x by 2 in the backward direction, and this is the electric flux density. This d is a function, this is the flux density, and this d is a constant on this front surface and the back surface. I'm just taking, and as this is a differential surface, so I'm assuming that this d is constant at the front surface and the back surface. So now I am considering about only the x component of d, because if I look into the front surface, the d will be along this direction, and for front surface the the dot product that survives is only dx dot dsx. So that's why I am considering this x component. So this is my x component of d at x plus x by 2, and for the back surface at this point, this is my x component of the electric flux density. So for the front and back surface, the field component which is of prime interest is the x component. And if you want to evaluate the left hand side of the Gauss's law, which is integral on that surface, on the closed surface, integral of d dot ds, ds is the differential surface element. This is the value of the electric flux density at the front surface, delta y delta z are ds. And this is for the back surface. This minus sign is because this integration is evaluated at the back surface, where it is directed, the unit vector is directed along minus x. So the result of this integration for front and back surface together will be like that. Now let us just recall one thing we have learned in our class 11 or 12 class. We have already learned that if we have 2 points where The two values of x coordinates are x and x plus h with a separation of x. Then we evaluate the function f at the corresponding points, and we can easily define del f del x or df dx rather, like this. This is a standard method of defining derivative of a function f. Now if we have another 2 points which is of which are separated by a distance of delta x. So for what we have defined here, for df dx, we can easily write in this situation that as limit of delta x tends to 0, value of the function at x plus delta x by 2 minus the value of the function at x minus delta x by 2 divided by delta x, and delta x tends to 0. So this is the standard definition of derivative, and we can write here this thing in the parenthesis as ddx of dx. For the timing, we are not making delta x equal to 0, but because we are rather interested in including this delta x by writing the whole thing as delta v, which is the differential volume element. Now for front and back surface, left hand side of Gauss's law gives me this. Why I have written the partial derivative, not the normal derivative? Because d is function of x, y and z. If it's a function of x only, we must write ddx of dx, but as this d is function of all the 3 variables, so we need to write this as partial derivative. For top and bottom surface, where dz, the z component of the flux density is of prime interest, because the unit vector will be along z direction and along minus z direction. So for top and bottom surface, we have this as a result of the integration, that is the left hand side of the Gauss's law. And for the right and left surfaces, dy is of my prime interest. So the result of the integration, that is the result of the left hand side of the Gauss's law, is like this. So the total result of the integration for the closed Gaussian surface will be like this. And if I just change the side of this delta v, I am taking this delta v on the left hand side. So I am writing this thing equal to limit of del v tends to 0, del v, where and this integration is this one. And this thing is entirely defined as the divergence of the field d. And the quantity in the left hand side is defined like this. We know that this is the del operator, and del operator is usually defined like this. This is the standard definition of the del operator. One thing I would like to mention, that I am not making here delta x equal to 0, because when we define df dx, that is the derivative of this function, this is the definition that delta x tends to 0. But when we do computation, we can't make delta x tends to 0. Rather, we have to choose the delta x to be a very small number. And this is called the numerical approximation of derivatives. This is very important. And here, while I'm writing the thing in the parenthesis as ddx of dx, I have just using that. I have just used that, and this type of numerical approximation of derivatives, these are quite useful when we will use the Laplace's equation. Our electric flux density has 3 components along x, y and z direction, and this is how I wrote the divergence of d. Now we have written this in our previous video, that this integration over closed surface d dot ds is equal to q enclosed, that is the total charge enclosed within this enclosed by this closed surface. So in place of this integration of d dot ds, we are free to write q enclosed. So this divergence of d eventually becomes limit of delta v tends to 0, q enclosed by delta v. And when I am writing q enclosed, that is the total charge enclosed by the volume, and making the differential volume tends to 0, I can easily call this one as rho v, or the volume charge density. So divergence of d essentially becomes rho v, that is equal to volume charge density, and this is the differential form of Gauss's law, and this is equivalent to the integral form of Gauss's law. And I just want to mention that the partial derivatives, that is del del x of dx, del del y of dy, and del del z of dz must be finite, and those derivatives must exist. Otherwise, this differential form of Gauss's law won't be valid. If we want that this differential equation, this differential form of Gauss's law must exist, then we must have finite non-zero values of these derivatives. In next video, we will be going to discuss Poisson's and Laplace's equation.